Okay, the first fundamental theorem of calculus says that if you have an integral from a to b of f of x, then this is equal to the indefinite integral evaluated at b minus the indefinite integral evaluated at a. And by the way, when you're evaluating the antiderivative for a definite integral, you do not add a plus c because, well, number one, you don't even know what it is anyway. And number two, when you do the subtraction, the plus c's cancel out. So there really is no point in adding a plus c to definite integral, and that's why you shouldn't. Now we're going to go over some properties of definite integrals. And a lot of these properties come from the fact that, well, an integral is a linear operation. So the first one is, if you have the integral from a to b, f of x dx. Oh my god, what was it? F of x dx. And suppose that you have some value c in between a and b, then we can split the integral into two from a to c and c to b. And the reason this works is, if you look at a graph, you're not actually missing anything by doing this. So if you have a here and b here, if you split at c, and so this is this area, this is this area, if you split at c and add them together, you're not losing anything as opposed to just doing the whole thing all in one part. And the second property that we're going to go over is the integral from a to b of f of x dx can be swapped with a negative sign to be from b to a f of x dx. I'll give you an example to show you why this works. Imagine that the integral from 0 to a of f of x dx is a, and the integral from 0 to b of f of x dx is b. This definite integral, we're essentially taking b minus a. That's this. But imagine we wanted to flip this order of subtraction. That's essentially what we're doing when we flip the bounds of integration. So we have a minus b equals the integral from b to a f of x dx. And introducing a negative on both sides, we get minus a, and the two negatives here cancel for a plus b, which is b minus a, which is the same as what we had before. We're going to do two examples of finding definite integrals. The first one is we're going to find the area under the curve of x squared plus 2 from 1 to 5. First, we have to find our antiderivative. So we're going to split this into two integrals. Like so. And when you split them, be sure to keep the bounds on every integral that you split into. And so now we're going to evaluate, well, first we're going to find the antiderivative. So using the power rule for integrals, we have, this is 1/3 x cubed plus 2x. And now, instead of adding a plus c, what we're going to do is we're going to draw this line. So we're going to evaluate this from 1 to 5. Same here. So this is signifying that you've performed the integration and now you're going to do the subtraction. Let's do this. I'll do it down here. So 1/3 x cubed from 1 to 5 is, you plug in 5 and you subtract when you plug in 1. Like so. So this is 125 over 3 minus 1 over 3, which is 124 over 3, which is not reducible. So we can go ahead and substitute this here. And now let's evaluate this. So same deal, we're going to plug in 5 and subtract and plug in 1. This is 10 minus 2, which is 8. So we can go ahead and substitute that for 8. And then I'm going to make this a fraction of 3, so we can add them easier. And this is 148 over 3, which is not reducible. Okay, now for the second example. So, like in the first problem, we're going to go ahead and find the antiderivative. Now, I'm going to keep this one together just to save space, but know that I'm evaluating this one at a time. So this is the integral of sine is negative cosine, and the integral of cosine is sine. And we're going to evaluate this from 0 to pi. When we do this, we get negative cosine of pi minus sine of pi, and all of this minus negative cosine of 0 minus sine 0. And now let's simplify. So this is negative, the cosine of pi is negative 1. This turns into plus 1. Minus sine of pi is 0. Minus cosine of 0 is 1. So this becomes negative 1. And sine of 0 is 0. So this 1 minus negative 1, so this is 2. And that's the answer to this problem. The area of under the curve sine x minus cosine x from 0 to pi is equal to 2. Okay, I'm going to wrap up the video by talking about the mean value theorem for integrals and how it relates to the average value of a function. So let's take a look at the mean value theorem first. It says that if f of x is continuous on some closed interval a to b, then it's guaranteed that there exists some value c such that the integral of f of x from a to b is equal to f of c times b minus a. What this is saying is, here, let's look at it on a graph. If I have this function, call this a, we'll call this b. So it's saying that since this is continuous on the closed interval a to b, it's guaranteed that there's some value, we don't actually know what it is from the graph, so I'm just going to say here, it's basically saying that there's some value such that the area of this rectangle is equal to the area under this curve. So at first glance, this theorem might not seem very useful. I mean, we don't even know, it doesn't even tell us what this value f of c is. But that's where the average value of a function comes in. Instead of just me telling you what the expression is, why don't we figure it out? Recall what an average is. An average is a sum of values divided by the number of values. So in this context, we're trying to sum function values in an interval and divide by the number of terms that we summed. So why don't we work out the sum first? And since you know addition, it doesn't matter any order, we can just label these values as f of x1 plus f of x2 plus f of x3 all the way until we have summed n function values. This is our numerator for our average. Now let's work out the denominator of our average. So we want to divide the interval from a to b into n equal subdivisions, and I'll call this length delta x. We're going to assume each of these x values are delta x apart. And this delta x is b minus a, the function width, over n, which is the number of subdivisions that we're splitting into. But we want to solve for n, right? Because we have n values up here, so we need to divide by n. So when we solve for n here, we get n is b minus a over delta x. So we can write this as our denominator. Notice how we can rewrite this with the summation sign. And we can simplify this complex fraction too, like this, where now this is being multiplied here, and this, I've just moved the fraction from the denominator to multiplication. Doesn't that look a little familiar? Think back to the first video. What's the definition of an integral? It's this, but with the limit to infinity. And we're trying to find the average value of a function, and for that to be as accurate as possible, we need to sum an effectively infinite amount of terms for this to be as accurate as possible and for this denominator to be accurate as possible. So when we take the limit as n goes to infinity, we get 1 over b minus a times the integral from a to b of f of x dx. And this is the average value of a function on the interval a to b. Remember how I said there's a relationship between this and this? Well, notice how we had the strange f of c here. What if we plug this into this? Then what do we get? So we have on the left, it's the integral from a to b f of x dx equals, now we're substituting this for f of c, 1 over b minus a integral from a to b f of x dx times b minus a. And notice this and this cancel, so that gives us integral from a to b of f of x dx equals integral from a to b of f of x dx. This is an identity, which means that this, the average value of a function, is f of c. So this is the same thing as here. The reason why that works is, notice how it's the mean value theorem. So another way we can interpret the mean or average value of a function is it can represent the entire function in this whole interval. Of course, that must mean the area under the curve from a to b of f of x dx is equal to this times the interval width, because average value of a function on an interval can represent the whole function on the interval.